In this video, we're going to look at continuous random variables. We're going to recognize and understand that continuous probability density functions, what they are in general. We're going to look at the uniform and exponential probability distributions and also the applications of those two. So what is a continuous probability function? Well, it is a graph of a continuous probability function or probability distribution is a curve. Now, when I say curve, that could be a straight horizontal line. The probability is represented by the area under the curve to the axes, the horizontal axes. So that's what the probability represents, is that area. The curve is also called the probability density function. That's a mouthful for me today, I guess. And it can be abbreviated sometimes as PDF. We use the symbol f of x to represent the curve itself, and that's because it's just a function and it's continuous. That means there's no jumps or holes or anything like that in the curve. F of x is the function that corresponds to the graph. We use the density function f of x to draw the graph of the probability distributions. And let's take a look at a histogram. Now, if I look at my histogram and I am measuring the height of plants, my histogram could have continuous variables, right? So I'm doing a measurement, so we know that is a continuous data. So my data is continuous. And so I would have from 1 to 2, and then I would have to decide where my class would end, just like we did in chapter 2. And then look at how many times I measured numbers between 1 and 2 for whatever plants I'm looking at. So you can see in this case, I have it happen 10 times. Now, if I were then to say, how is that related to the probability? If I take the thing that it happened 10 times and I divide it by the total number of data pieces, I would get a probability. I would get that relative frequency. So if I were to take this 10, happens 10 times, divided by however many data pieces I have, this would be that relative frequency, or in other words, the probability. Now, if we want to know the proportion of plants that are between 5 and 8 inches, we will sum the areas of the two rectangles, 5 and 6. So here is between 5 and 6, and 7 and 8. And then this area would be the frequency of each one with a width of 1. And each height of the rectangle is the frequency. So what we know then is that this area here would be 4 out of 6, because I've got 3 plus 1 more is 4, and there's 26 pieces of data. But if we wanted to know the probability of choosing a plant between 5 and 6 inches tall, we would need to sum the probabilities of choosing those two groups. And that answer would be 0.1539, which just happens to be 4 divided by 26. So this area and this area, if I were to add them up, I have a width of 1, a height of 3, and a width of 1 and a height of 1. I get 4 out of 26, but those areas give me 4 out of 26 bars, which the probability then is 0.1539. So that's really kind of nice. We've been doing probabilities all this time. We just didn't call it that because we weren't ready to. The area under the curve is given by a different function. We call this the cumulative distribution function, abbreviated CDF. The cumulative distribution function is used to evaluate probabilities as area. The outcomes are measured, not counted. The entire area under the curve above the horizontal or x-axis is equal to 1. The probability is found for intervals of x rather than for individual x values. So as an example, we have the probability that x runs between c and d, and that would be the probability that the random variable x is in this interval between c and d. And it's the area under the curve above the x-axis to the right of c and to the left of d. So let's go back up to my example up here. So if I want the probability of getting one that is between 5.6 and 7.8, there's my interval. So I have a probability of the value I want is between 5 inches tall and 8 inches tall. then that would have been this area, which is this area, which is 4 out of 26, but it's also 0.1538. So that's what it means to be the right of 5, but to the left of 8. Right of C, left of D. So if I want the probability of getting exactly C, this is 0. And the reason this now is 0, and it wasn't in chapter 4, is because I'm looking at the area underneath a particular value. So what is the probability of getting, what's the probability of getting exactly 5? Well, here's about 5. And I drop down and there's no area. It's a straight line. There's nothing there. So that's why in these types of probabilities, it will be 0. The probability of X being between C and D is the same as equality, because the probability is equal to area. So we don't worry about the less than, strictly less than, and the strictly greater than in this type of distribution. The probability of C being less than X is the area to the right of C that I'm looking for. The probability of X is less than D is the area to the left of D, is what I'm looking for. The probability is X is less than C and X is greater than D. That means that I'm looking for the left of C added to the area to the right of D. So we want to think of that as kind of like tails. So if I were to draw, say, some shape, this is some distribution shape. Here is C, here is D. If I wanted the probability of X being less than C and X being greater than D, then I would be looking for this area under the curve. So here are some examples. Here is a uniform distribution in which I want to know the probability that I'm between 3 and 6, and so this is what the graph would look like. If I wanted, here's a normal distribution, the bell curve. If I wanted to know what is the probability that the thing I'm chasing is between 1 and 2, then this is what it would look like. If I'm in the land of exponential distributions, an exponential distribution is a curve that starts fairly high and then goes down close to, but not including, equaling 0. And so if I wanted the probability between 2 and 4, this is what it would look like on the exponential. What is a uniform distribution? Well, uniform distribution is a continuous probability distribution, and it also has any event are equally likely to occur. When working out problems with a uniform distribution, we need to be careful to note if the data is inclusive or exclusive. The notation for the uniform distribution is, here's my random variable X, is approximately a uniform distribution where I need A and B. A is the left side and the smallest number, B is the right side and the highest number, and of course X would be in there somewhere. The probability distribution function is defined as f of X is equal to 1 over B minus A. So this also gives us the height of the function. So if I come back over here to my picture, then the height of this line is going to be f of X. And in this case, because I start at 2 and end at 9, it's going to be 1 over 9 minus 2. So it's going to be 1 over 7. So that's the height, and it's a constant. So the height of this is 1/7. The formulas for the theoretical mean and standard deviation is mu is equal to a plus b divided by 2, and sigma is the square root of a minus b, the quantity squared, divided by 12. Make sure you have that on your notes somewhere. So for the function f of X is equal to 1 over 20 between 0 and 20. Now I can tell you where they got the 1 over 20, because remember we are using f of X is equal to 1 over my b minus a. Here is b, here is a. Construct the graph. Okay, well, so here's my graph. I'm going to call this y, I'm going to call this x. I'm going to start at 0, I'm going to end at 20, and then its height, how far up I'm going to go, is going to be the line is equal to 1 over 20, or in other words, f of X is equal to 1 over 20. So if I wanted to know the probability between 1 and 5, well, Here's about 1 and here's about 5. So I just need to multiply this distance times its height because it's just a rectangular shape, and that's going to give me the area under the curve. So this is just going to be the distance I've traveled, which is 4, so 5 minus 1, multiplied by 1 over 20. So I get 4 multiplied by 1 over 20, so 4 over 1. So I get 4 over 20, which is going to be 1 and 5. So about 0.2 is the probability. Now, what is the probability of x being less than 10? Well, so here is 10, and I want this entire rectangle. So this would be equal to 10 minus 0 multiplied by the height, because this will give me the length of the box, this rectangle. This gives me the height of the rectangle. And so this is just going to be 10 over 20, or in other words, 0.5. That's not too bad. So here's an application. Bus wait times are uniformly distributed between 7 and 14 minutes. The unshaded rectangle below with area 1 depicts this. Oh, do I have that? No. So let's go ahead and draw that then. So again, I'm going to go ahead and move that way over there. That's not what I wanted to do. My apologies. So I'm going to go 7 to 14. 7 to 14. So I need to figure out how high I need to go. So my f of x is going to be 1 over the 14 minus 7, which is 1/7. So the height of this is 1/7. So this is y is equal to 1/7, which is also f of x. And that would be my uniform distribution. The shaded rectangle depicts the probability of selecting between 8 and 13 minutes. Okay, well, here is 8 and here is 13. So this is the rectangle I'm looking at. And so if I want to know the probability between 8 and 13, then I just figure out how far I've traveled, which, the length of my rectangular box, which is 13 minus 8. Then I'm going to just multiply by that by 1/7, and then whatever that is the probability that you will randomly select a bus wait time between 8 and 13. The exponential distribution is often looking about the amount of time until someone has a specific event occur. So this is not like uniform distribution, and I have a different shape. For an example, the amount of time starting right now until an earthquake occurs is an exponential distribution. Other examples include the length in minutes of how long distance business calls are, the amount of time in months the car battery lasts, something like that, where you're looking at something over time. Values for the exponential random variable occur in the following way. There are fewer large values and more smaller values, and that's because the shape of the curve. So the shape of the curve is going to look something like this. It's actually going to start like that and go down. So as time runs out, further out in this direction, as we go out in that direction, in the positive x direction, the positive horizontal direction, we're going to get closer and closer to 0, but not quite ever reach 0. So example, the amount of money customers spend in one trip to the supermarket follows an exponential distribution. There are more people who spend small amounts of money and fewer people who spend large amounts of money. The notation is x is approximately distributed as an exponential m, where m is the decay parameter. And you're like, oh, this is interesting. Where is this coming from? We'll get there. The exponential distribution is widely used for the field of reliability. Reliability deals with the amount of time a product's last. So the probability distribution function looks like this, where it's going to be m multiplied by e raised to the negative mx. And e, by the way, is just a number. E is in our calculators. It's actually in our spreadsheets, and it's approximately equal to 2.72. It's just a number. So how do we get m? Well, we're going to have this mean, and m is going to be 1 over the mean, mu, or mu is equal to 1 over m, depends on what you have. The standard deviation is mu. The cumulative distribution function is going to look like this, where I have P of X is less than X, P cap X is less than X. 1 minus E, which is just a number, raised to the negative XM. So additionally, the probability of X being greater, the probability of cap X being greater than X is E raised to the negative MX. If I want to run between two of them, I'm going to have E raised to the negative AM minus E raised to negative B. And lastly, if you want a probability of an interval around a mean, then you have this lovely, lovely formula. Now, before we jump into all of this example here, which will be phenomenal, I would recommend you have some sort of spreadsheet that looks like this. So A is the left number, B is the right number. Then we're going to calculate the height. Mu is the mean, and its calculation is here. Sigma, which is a standard deviation, is here. I didn't put variance. I should have done variance. C is some number between A and B. C is the number that you are usually looking at. D is some number where it is C, then D, then B. So we have a starting point. We have our ending point. This is a point of interest, and this is some other D value. Here's my f of x, and to find this, what I did was I did an equals, and then I did 1 divided by. I grabbed this cell, which is the B cell, subtracting off this A cell, and so here is my height, or in other words, my uniform distribution function. Mu is going to be A plus B divided by 2, so I did an equals. I took A plus B, make sure I had parentheses in the right places, and divided that answer by 2. Sigma is going to be the square root of B minus A, the quantity squared, divided by 12. So I did an equal symbol and making sure I grabbed the A cell, the B cell, and then made sure I had all my parentheses in the right places. The probability of being less than C, where of course that C is some number between A and B. So the probability of being less than C is going to be C minus my beginning A times my height. So that's in the spreadsheet. I did an equals, parentheses. I grabbed the cell that had C in it. And then I did another parenthesis, or I did, minus the cell that had A in it, into the parentheses, and multiplied by my height here, which is my uniform distribution function. If I want it greater than C, then what I'm going to do is I'm going to take equals, and it'll be D minus, and that should be C. D minus C, not B. And so I would take the B value. So I would do an equal symbol, parenthesis, my ending point B, subtract off C, this is this, and parenthesis, and multiplied by f of x. The probability of exactly C is 0. It's always just 0. Now, if I wanted the probability that is between C and D, and they're not the ending and beginning points, then again, I'm going to do an equals, a parenthesis, D being the larger number, so I do D, and then that cell minus this cell, parenthesis, and then multiplied by the height. So if the probability, if you're given the probability and you're looking for C, you're going to have this, the probability of X is greater than C will be given to you. To find C, then you're going to have a cell that's going to be B. You have to know what your B value is. You're going to have B minus, and then you're going to have this number right here divided by the f of x function. So you'll need to know A and B still to be able to figure out what C is. But if you're given the probability of C happening and you're given A and B, you should be able to go backwards and say, well, C would have to be B, the ending point, minus the probability of the X greater than C divided by the distribution, the uniform distribution function. Similarly, if we have P of X is less than C, then what we would put in this cell would be A plus, because we need to know A, plus the probability of X less than C divided by f of x, where we have these numbers that we are going to enter. Now, exponential distribution. A is some number, B is some number where it's bigger than A. The function, which is equal to the height, not uniform, is equal to E, which is an EXP in a spreadsheet, and then raised to parenthesis negative mx, where m is equal to 1 over mu, and mu is the mean. So you'd have to know an A, and you might be given a B, you may not, it may be just A, and you have to be given a mu. So then m is going to be calculated as 1 divided by mu. So I did an equals here, and I did 1 divided by this cell. My f of a, here I need to do the exponential, right? So we have an exponential, this exp is the e number, and it's going to assume that you're doing e raised to whatever you put in here. So to do this calculation, I'm going to do an equal symbol. So in this cell, I did an equals exp. I put a negative there, so a minus or a negative. And then I grabbed my M cell and I multiplied it by my A cell. And there's the probability of A, the probability of B. Here's the probability of X less than A. So it's 1 minus, because we know the entire area has to be 1. So we have 1 minus F of A. If we want it greater than A, we're going to do just F of A. Because when we're doing our probability distribution functions for the exponentials, by default, it's when we do the exp negative m multiplied by a, that is f of a. And then if I want it less than b, it's 1 minus f of b. So I'd have to have f of b in here too. And then to be between the probability of b less than a. So we do the b, and then we do less than a, because b will be a larger number as a value is the probability, so it needs to be the probability of B happening minus the probability of A happening. So you're going to need this spreadsheet. I would recommend that you have something similar. You have whatever you want, but I would suggest something similar. At the very least, I suggest you get these numbers and make sure you're getting the same numbers that I am personally getting on this spreadsheet. Now, let's actually go back and do this application. So find f of x. The average time it takes a salesperson to finish a sale on the phone is 12 minutes and is exponentially distributed. So they're telling me that mu is 12. That's the first thing. So this mu is mu, not m. Mu is 12. That means m is 1 over 12. So my function, my probability function, is e raised to the negative x over 12. So what I'd have to put if I was trying to do this calculation is I would do in an Excel spreadsheet, I would do equals exp negative, and I would have an x, and then I would have my m, whatever that is calculated. So I want to know less than 10 minutes pass before a sale is completed. So what I'm asking for is P is X is less than 10. So this is going to be 1 minus E raised to the negative 10 divided by 12. And in this case, I have the 0.56. I don't know what happened there. 0.5654. We want to know more than 10 minutes pass before it's completed. So more than 31 minutes. So this is P is X is greater than 31. And this is simply going to be E raised to the negative 31 over 12, which, again, using the spreadsheet, I'd have 0.07552. If I wanted to know between 10 and 31 minutes passed, then I'd be looking for the probability of 10, which is less than x, which is less than 31, which is the probability of x less than 31 minus the probability of x less than 10. And you're thinking, shouldn't it be greater than 31 and minus 10? No. So if you remember here, that it's this. And also if you look down on my spreadsheet, that's what I'm doing. So I would do these two probabilities, and when I got done, I end up with 0.3591. Now let's take a look at our last example here. Within 8 minutes of the average time it takes before a sale is completed. So this one is slightly different, and in fact what we're going to be using is this one here. If you want to find the probability of an interval around the mean, then this is what we're going to use. We're going to use E raised to the negative mu minus X over whatever time unit I have divided by mu, and then minus E raised to that. And then I should have put that on my spreadsheet and I didn't. So what we're going to do is we have to talk a little bit about what this time unit was. I have 12 minutes and I have 8 minutes, so they're in the same units of time. Had this been in 12 hours and this would have been in 8 minutes, then this time unit would have been the thing I needed to do to convert. So let me explain. Say my mu was in 12 hours, right? And I'm asking to be within 8 minutes of that. Now these aren't the same units. So to do that time unit to convert, I would have said, how do I get from minutes to hours? So that exponent would have been 12 minus 8 divided by, well, there are 60 minutes to an hour. So that time unit is what converts so that I'm talking either all hours or all minutes. So that's what that time unit is. Because of the fact that my time unit here is both in minutes, I don't have to divide by anything other than 1 if I want to. So the formula I'd be finding would be e raised to my mu, which happens to be 12, minus 8. And I don't have to do anything with the 8 because they're both in units. And then it's going to be divided by my mu, which is 12. Then I have minus e raised to the negative 12 plus 8 divided by, parentheses, divided by 12. And I put all this in my spreadsheet, and I'm going to get 0.5276. 5, so I make that 7. So I'll make that a 7. Now I'm going to go down to my spreadsheet, and what I should put in here is the exponential distribution, and I want to know when I'm around my mean. So I might have here when finding the probability around the mean. So the mean, not my mean, the mean. Around the mean. Okay. So once again, I would still have my mu. So I would have my mu here. Mu. And I could just do an enter from this cell up above, or I can just enter it. So with the formula I just did, I had my mu was 12. So I'm going to enter that. So I'm going to do that in green. So let me highlight that in green. So that tells me I'm going to enter value. And then I might have what I want to be within. So I'll call that, what do we have, x before? And I'm going to enter value. And again, I'm going to put that as green because that's something I'm going to enter. So I'm going to enter that value as well. And remember, x is the thing we want to be within, right? So I want to be within so many minutes. And then I'm going to do my time unit here. So I'm actually going to put time unit. And because this is minutes to minutes, my time unit, my conversion is just 1. So again, I would have a green box, and I would enter this. So I might also off to the side say use 12 if years and months are given. Use 60 if minutes and hours are given. So something like that to remind me that's what I'm going to put in there for my time unit. All right, so my x for my example up above was an 8. These were, and I should say use 1 if the units in mu and x are the same. So I'd label this kind of stuff because I want to know later what the heck am I supposed to be putting in here. All right, so the formula from up above would have been e raised to the negative mu minus the x divided by time unit. And then that gets divided by mu again, and then I have a minus e raised to the, and then the only difference is mu plus the x divided by time unit, and then divided by mu. So I might do intermediate steps, and so I might do here mu, a negative mu minus x divided by time, and then divided by mu again, and then equals. So that's really messy. But I would do something like that. So I'm going to erase this, and I'd back it up a little bit. All my green, by the way, all of my green should have been lining up. And so I would do a negative mu, parentheses, mu minus x divided by time, divided by mu. Okay, so I would then have a box here, but it's not going to be green because I would actually be grabbing the cells that do all of that, right? So I do an equals and grab all those cells. Then I would do a negative mu, parenthesis, plus x divided by time, parenthesis, divided by mu. And then I'd have another bar here. And again, I'd have all of these lining up here, like here. And then my last one would have been e raised to the negative mu minus x divided by time, divided by mu. And then minus e raised to the mu minus plus x divided by time, divided, parenthesis, divided by mu. Okay, so let me give you the numbers that I got by doing the x minus, or mu minus x divided by the time divided by mu. So for this first cell using these numbers, I've got 0.333. And then for this next one, using these numbers, I get 1.6 repeating, so 1.66, and I'll do a 7. And then my next and final bar here would be an equal sign, and I would be using, when I was filling it in this cell, I would be doing equals, and I'd type in EXP, and then I would grab the cell that had that minus EXP, and I'd grab the cell that has that, and it already has a minus on it. And when I got done, by the way, my answer was, my answer when I totally got done was 0.5276, so I'll do 28. And that would be my final answer. So I would probably need to add that to my spreadsheet for this section. And that's it. This is all of chapter 5. We are almost halfway through the material that we need to cover, and we're almost halfway through the quarter at this point too. So we'll see you in class.